Hello everybody, welcome back to the lecture on first module of Applied Electromagnetic Theory. Myself, Shama Srikumar, Assistant Professor, Department of ECE, Rajagiri School of Engineering and Technology. Now we'll be continuing with the topics in magnetostatics. The topics covered in today's lecture will be magnetic flux density, fourth Maxwell's equation, magnetostatic energy density, and the boundary conditions in magnetostatics. So we have already discussed about electric flux density as the electric flux per unit area. Similarly, magnetic flux density is obtained from magnetic field intensity. So the magnetic field intensity H was determined using the Ampere's circuital law. So using this H, it is dependent on the properties of the medium, that is the permeability or mu naught. So we are defining a new vector quantity which is B, which is defined by mu naught into H. So this B is called as the magnetic flux density, and mu naught is the permeability in free space, and H is the magnetic field intensity. And B is measured in Weber per meter square. That is, it is the flux per unit area, so it is measured in Weber per meter square. So the value of mu naught was 4 pi into 10 raised to minus 7 Henry per meter. Now, when you consider the magnetic flux density V, if you want to find the total magnetic flux through a surface S, we will integrate it over the area. So psi, which is the magnetic flux, is given by integral S V dot ds, and the unit of psi is Webers. So when you consider magnetic flux line, it is a line to which the magnetic flux density is tangential at every point. That is, the flux density will be along that line. So if you are having a magnetic compass, this line will be the line along which the needle of the compass will be placed. That is, the north pole of the magnet will be pointing in that direction. That is, the north pole will always orient in the direction of magnetic flux. Now, when you consider a direction here, this is a north pole. So, this will denote the direction of magnetic flux density. So, if you are having a straight current carrying conductor, this is a current carrying conductor which is carrying current out of the plate. So, according to the right hand thumb rule, if you place the thumb in the direction pointing the current, the fingers will curl around it. Thus, that will give us the direction of magnetic flux lines or magnetic flux density. When you observe those lines, they will be always closed, and also they won't cross each other. Because they will be concentric circles. That's at whichever point we measure, that will be a circular path. So in this, it is current is carrying outward, so the magnetic flux line will be in the anti-clockwise direction. So we will compare the properties of magnetic flux lines with the electric flux lines which we observed in electrostatics. So when you consider a positive charge, the electric field lines or electric flux lines will be pointed in the outward direction. That is, this is a positive charge, so the field lines or flux lines will be radiated outward. So when you consider in electrostatics, according to Gauss law, we know that if you are having a closed surface, the amount of flux lines crossing that closed surface will be equal to the charge enclosed. That is, closed integral S d dot ds is equal to charge enclosed. That was the property in electrostatics. And when you consider electric flux lines, they are not closed. That is, when you consider a positive charge, it will act as a source. When you consider a negative charge, it will act as a sink. That's all the flux lines will be coming towards the negative charge. So when you consider electric charges, we are possible to have isolated electric charge. That is, we can have a positive charge and a negative charge separately. But when you consider magnetic flux lines, it will always, that is the magnetic poles, that is North Pole and South Pole will always exist in pairs. We can't separate the North Pole and South Pole. So when you consider the direction of magnetic field lines for a bar magnet, it will be directed from the North Pole and it will end at the South Pole. Actually, when we find in the interior path, it will be returning from south to north. That is, the magnetic field lines will be always forming a closed path. So if you form a closed surface along one of the poles, the net magnetic flux lines crossing that pole will be equal to zero. Since the flux lines coming out will also be coming in, so they will cancel out each other. So the net flux crossing a closed surface S around a magnetic pole will be equal to zero. That is, psi is equal to closed integral S B dot ds will be equal to 0 in the concept of magnetostatics. Here we can't separate, that is, we can't have isolated magnetic poles, that is, we can't have North Pole, South Pole separately as in the case of electric charges. So that is the difference between the electric flux lines and magnetic flux lines. So we told that we can't have isolated magnetic poles. What will happen if we break a bar magnet? That is, we are having a bar magnet which is having a north pole and a south pole. So this is a bar magnet with north and south pole. I'm making it into two halves. So when you divide it into two halves, each half will be having a north pole and south pole. That is why we are telling that we can't separate the magnetic poles. As we go on dividing the magnet, each portion of it will be having a north as well as south. One end of the magnet will be north, one end of the magnet will be south, independent of the length of the magnet. So the successive division of bar magnet will form bar magnets with both north poles and south poles. So the magnetic poles can't be isolated. Therefore, an isolated magnetic charge will not exist in the case of magnetostatics. So that is the property in magnetostatics. So now we will be discussing the magnetic equivalent of Gauss. So we are considering a closed surface around one of the poles in a magnet. So when you consider the closed surface, the amount of flux crossing that closed surface will be equal to zero. It is because whatever the flux is coming out is coming in the opposite direction through the inner of the magnet. Therefore, according to Gauss law, the total magnetic flux around a closed surface will be always equal to zero in the case of magnetostatics. That is, psi is equal to closed integral S B dot ds, and that is equal to zero. So this is called as the law of conservation of magnetic flux. That is, whatever flux is coming out is also coming in, and hence the net magnetic flux is equal to zero. So when you consider this equation, if we apply the divergence theorem, the closed surface integral will be equal to the integral of volume of divergence of magnetic flux density. So this closed integral as B dot ds will be equal to integral over volume del dot B d, and that is equal to 0. Therefore, we can conclude that del dot B is 0. Thus, the magnetic field lines doesn't have any source or sink, and they will always remain closed. So that is the property of magnetic flux line. Hence, we have derived the last Maxwell's equation or the fourth Maxwell's equation as the Gauss law for magnetostatics. The integral form of that equation was closed integral S B dot ds equal to 0, and the differential or point form was given by del dot B equal to 0, which was obtained after applying the divergence theorem. And this theorem as a statement states that the net magnetic flux crossing a closed surface is equal to 0, and also we can conclude that isolated magnetic monopoles does not exist. Next, we'll be deriving the expression for magnetostatic energy density. For deriving the expression, we'll be considering a differential volume which is placed in a magnetic field B. So this is a cubical structure which is placed in a magnetic field B, and the sides of this differential volume is given by delta x, delta y, and delta z. Now, this volume is covered with conducting sheets on top as well as bottom. So this top portion is having a current of delta I, and this bottom portion is also having a current delta I. That is, through the top it will be carrying through the bottom. So top sheet and bottom sheet is covered with conducting sheets with current delta I. Now these two are marked as the conducting sheets. All the others are non-conducting. Now when you consider the whole volume, the amount of inductance that each volume will be carrying in terms of flux can be given as delta L is equal to delta psi by delta I, because according to the property of inductance, psi will be equal to L into I. So delta L will be equal to delta psi by delta I. Now, what is the flux? Flux is equal to the flux density into area. That is, it is integral as B dot ds, but here we are considering a small area, so it is B dot ds divided by delta I. Now, what is this B? B is the magnetic flux density, which is in the y direction. So as you all know, B can be expressed as mu into h, and it is in the y direction, so we are having AY cap dot the area through which the magnetic flux lines is crossing. So it is crossing through this side face. So when you observe the area, it is equal to delta x into delta z. So when you multiply this delta x, delta z, ay cap. So as you all know, ay cap dot ay cap, it is 1. So you will get it as mu h delta x delta z by delta I. And that is the value of the differential inductance observed here. Now, to find the current carried by the conducting sheet, we are going to apply the Ampere's law. So according to the Ampere's law, closed integral L h dot dl is equal to the current. So on applying the Ampere's law, this current delta I can be given as the product of H and dl. So what is H? It is in the direction of magnetic flux density. So as a vector, it is magnitude H into AY cap. Now, what is the differential length we should take? That is, we should take how much of the current is along this direction. So we should multiply it with delta y AY cap. So as you know, AY cap dot AY cap is 1. So you will get the current enclosed by this magnetic flux lines as H into delta y. So this is the value of delta I. Now to find the energy, you know that the energy stored in an inductor is half Li square. So the magnetic energy stored in this is given by delta Wm, which is given by half delta L delta I square. Since we are considering a small differential volume, we will be putting the symbol delta everywhere. So we have already determined the value of delta L as well as delta I. On substituting that, you will get it as half mu h square into delta x, delta y, delta z. So this is the magnetic energy stored within an inductor. So we got the magnetic energy stored in joules within the field of an inductor as half mu h square delta x delta y delta z. So when you consider delta x delta y delta z, it is the differential volume of that structure. So this can be replaced as delta Wm is equal to half mu h square into delta V, where delta V is the differential volume. Now, for finding the magnetostatic energy density, it is the energy per unit volume. So, to finding magnetostatic energy density given by small wm, it is delta Wm by delta V. And we have to make this delta V tending to 0. That is, we should consider a small differential volume. So, as we apply this limit, we will get Wm as half mu h square. Now, what is this h in terms of b? We know that h equal to b by mu. So when you substitute that, we can replace this expression as b square by 2 mu. Also, we can also express in the terms of half b dot h. That is because B is equal to mu H. So mu into H dot H is same as mu H square. So in these three forms, we can express the magnetostatic energy density either as half mu H square or B square by 2 mu or half B dot H, and it is the energy density measured in joules per meter cube. That is, it is the energy per unit volume. So next we'll be discussing the boundary conditions for magnetic field. So when you consider the boundary condition, we already told that when a field crosses from one medium to another, what are the conditions should to be satisfied at the boundary. So that denotes the boundary conditions. So to apply the boundary conditions, we are using the two Maxwell's equations for magnetostatics, which is given by closed integral S B dot ds equal to 0, and the other equation is the Ampere's law, which is closed integral L H dot dl equal to I. Using these two equations, we will be deriving the boundary conditions for magnetic fields. So for deriving the magnetostatic boundary condition, we are considering the magnetic field vector H. As we did in electrostatics, we are dividing it into the tangential and normal components. So the tangential component is given by ht and the normal component is given by hn. So the vector H, magnetic field intensity, can be split into ht and hn, where ht is a component which is parallel to the surface and hn is the component which is normal to the surface. Thus, the total magnetic field H can be written as H equal to ht plus hn. So, for deriving the boundary conditions in magnetostatics, we are considering two mediums with permeability mu1 and mu2. The magnetic field intensity in medium 1 is H1 and the magnetic field intensity in medium 2 is H2. So this component H1 is split into the tangential component H1t and the normal component H1n. Similarly, H2 is split into H2t and H2n. So the total magnetic field intensity in medium 1 is written by H1 equal to H1t plus H1n, and the total magnetic field intensity in medium 2 is given by H2 equal to H2t plus H2n. Now to apply the Ampere circuit law, that is closed integral L H dot dl equal to I, we need to consider a closed path. So we are having a closed path A, B, C, D, A, which carries current in the boundary. That's it's enclosing the current at the boundary, and this current is in the inward direction. So when you apply the right hand thumb rule, the thumb pointing in the inward direction, the fingers will curl around in the clockwise direction. So that is the magnetic field setup due to the current density K at the boundary. Now we are considering the path to be very small, that is the dimensions delta W and delta H are very small, and the components of magnetic field intensity will be constant along this entire path. Now this current density K is the current per unit length. That is, it is measured in ampere per meter and it is perpendicular to the boundary. Now, when you apply the Ampere circuit law along the sides of the boundary A, B, C, D, A, so we'll start from A, move till B. So it is in medium 1, so that is parallel to the boundary, so it is H1T into delta W. So when you move from B to C, half is in medium 1 and half is in medium 2, so it is minus H1N into delta H by 2 minus H2N into delta H by 2. Since it is in the normal direction, we are taking the normal component and half the height will be taken. Now when you move from C to D, it is parallel to the boundary, so it is the tangential component. So it is minus H2T into delta W since they are in opposite direction. Now when you move from D to A, we are having the normal component, so it is plus H2N into delta H by 2 plus H1N into delta H by 2. And that will be equal to the current enclosed by this path A, B, C, D, A. Now, what is the current enclosed? It is measured in terms of current density, which is in ampere per meter. So, what is the length of this boundary? It is equal to delta W. So, if you multiply the current density by delta W, we will get the current I. So we'll do K into delta W. Now on cancelling the terms, we are having H1 and delta H by 2 minus H1 and delta H by 2. It will get cancelled. This H2 and delta H by 2 and this H2 and delta H by 2 will get cancelled. Now the remaining terms are H12 minus H2T is equal to K. So when we observe that if we are having a current at the boundary, then the tangential component of H is given by H1T minus H2T equal to K. Now, if you extend that derivation by considering the boundary current to be 0, that is K equal to 0, then the first boundary condition H1T minus H2T equal to K reduces to H1T equal to H2T. That is, the tangential component of magnetic field intensity is continuous across the boundary separating two medium with different permeability. Now we know that B equal to mu into H. On substituting this equation into this, we will get it as B1T by mu1 is equal to B2T by mu2. From this equation, we can conclude that the tangential component of magnetic flux density will be discontinuous across the boundary of two medium of different permeability. Now, for finding the relation between the normal components, we are considering a cylindrical surface. That is, we will be considering the cylindrical Gaussian surface as we considered in electrostatics. So this surface is having a high delta H which is very small, so that now we should not consider the magnetic flux lines along the curved surface of the cylinder. The top and bottom surface is having an area of delta S, and we are having the flux lines which is coming out to the top as well as the bottom surface. Now, when you use the Maxwell's equation, that is the closed integral S B dot ds equal to 0. That is the Gauss law for magnetostatics. So this closed surface is made up of the top surface, bottom surface and the curved surface. Through the curved surface, we can neglect the field component. So considering the top surface, it is in the first medium, so the component is B1n, and for the second medium, it is B2n. So this can be written as B1n into delta S minus B2n into delta S. So since the area vector of bottom face is in the downward direction, this is minus B2n into delta S. This is equal to 0. So since the delta S get cancelled off each other, we will get B1n equal to B2n. That is, the normal component of magnetic flux density is the continuous across the interface. That is, Bn will not undergo any change when it moves from one medium to another. So we got the equation B1n equal to B2n. Now we know B equal to mu into H. Substituting that equation, we will get mu1 into H1n is equal to mu2 into H2n, since mu1 is not equal to mu2. Thus, we can conclude that the normal component of magnetic field intensity is discontinuous across the interface between two media. That is, the normal component of magnetic field intensity will undergo a change when it moves from one medium to another. So these are the boundary conditions related to magnetostatics. Now, to find the relation between the angles made by the flux density components with the perpendicular, we are using these two boundary conditions. So we are considering a boundary which is free of current, and the inclination of B1 and B2 with the vertical is given by theta 1 and theta 2. So according to the first boundary condition, H1T equal to H2T. Now, when you're finding the tangential component, it is actually the sine component, because when you consider the tangential, it is opposite to theta. Similarly, this tangential is also opposite to theta, so it is H1 sine theta 1 is equal to H2 sine theta 2. Now, the second boundary condition relating the normal component is given by B1n equal to B2n. As you all know, B is in terms of H is given by mu into H, so it is mu1 into H1. Now, the normal component is a site adjacent to theta. So it is represented by cos. So it is mu1 h1 cos theta 1. It will be equal to mu2 h2 cos theta 2. On dividing the two equations, we will get tan theta 1 by mu 1 to be equal to tan theta 2 by mu 2. Thus, we can conclude that tan theta 1 by tan theta 2 will be always equal to mu 1 by mu 2. So here mu is the permeability, total permeability of medium 1 and 2 respectively. So mu can be replaced by mu naught mu r. So this expression can be replaced as tan theta 1 by tan theta 2 is equal to mu r1 by mu r2. And this is the law of refraction of magnetic flux at a boundary which is free of current. So we'll conclude this lecture on magnetostatics, and we have discussed about the Gauss law for magnetostatics, the magnetostatic energy density and the boundary condition for magnetic fields. Thank you.